Spencer.
All right, so it says find the point of the parabola at which that 0.14 is going to be the closest. So in order to find the closest point to another point on the graph, we need the distance formula. So the distance formula is the square root of x minus x1 squared plus y minus y1 squared. So what I did was plug in x1 and y1, which are 1 and 4. So we are trying to minimize.
How did you get to that?
We're trying to minimize a distance. In order to minimize or maximize, the other day we talked about how we have to get everything in terms of one variable. So currently in the distance formula you have x and y. Well, we can't have two variables because that would have two derivatives into our problem. So what I did was I said, well, y is really just x squared. So I substituted x squared for the y. So now I was able to transform my distance formula to be in terms of one variable. As I said, I was like, I'll get there. Like, you'll see it. So then I said to myself, I really don't want to take the derivative of square root. So how can I make that better? By squaring both sides.
Did you factor it now? Just factor out your terms?
I would just spoil it because I don't want to take the chain rule of a derivative, but either way, you're good. So you can either take the derivative using the chain rule, or you can FOIL.
Both easier to use the chain rule?
Yeah, I was going to say, like, both are they're pretty much the same. Like, you end up with almost similar lines, because if you FOIL it and then derive it versus the derivative and then the chain rule, either way you still have to like distribute and combine like terms. So it's really just more of what you're comfortable with. So I typically do the chain rule because I tend to make like FOILing mistakes, especially when I have a difference of squares. And then what's nice about doing the chain rule is it's kind of like Pythagorean theorem. All of the 2's cancel. Yep.
Why do you have to multiply by d?
Because the derivative of a derivative is like if you have y squared, its derivative is 2y dy dx. So this is like a d squared instead of a y.
Well, if all these students, please report to the office. Michael West, Tyler Hill, Austin Wheeler, Dylan Coomer, Nathan Scheib.
That was for
Xavier
related
Pista,
rates.
Marcus
So
Prize,
if it
Dan
asks
Anderson.
you about
Those
change
students, please
in
report to the office.
time.
Okay.
So only if a problem refers to time do you do a d whatever dt. Since these don't have anything to do with time, we don't do any ddt's. I know that's the hardest part about going from related rates like back to these types of problems, because it's hard to remember how to derive without the dt's.
Okay, thank you.
You're welcome. So now we just need to clean this up algebraically. So you'll distribute your 2x.
Why would I randomly switch to green?
So you get x minus 1 plus 2x cubed minus 8x equals, and again combining like terms, 2x cubed minus 7x minus 1, which is what type of equation?
Cubic. Oh. Cubic.
Yep. So we don't really have like a good formula for cubic. And then technically all of this is over, because this was d times d prime. Technically all of this is over the original distance formula still. So how do you minimize or maximize a problem? Where do the mins and maxes occur?
The zeros.
The zeros of the derivative. So what we have to do is find the zeros of our derivative. Can a min or max occur at a zero of a derivative that does not exist? So if you have a DNE, it still serves as a critical point, right? So this would definitely be a calculator problem because this is gruesome. So your roots, you would take your calculator, you would type that in. So we know how to find the zeros of a problem on the calculator, or is this something you want to take a minute and type that equation in and find them?
You could type in the equation and just figure out where it intersects.
What's it?
Intersect?
Not intersects, but
There's like, you'd go second, trace, and go to zeros. So that's what I'm saying, like we know how to do it on the calculators, we're good. So that's what you do, you type that into y1, and then you look at the graph, and you would go, okay, second trace, and then you would find your zeros. Yes?
I'm still a little confused on why it's over the distance formula. I mean,
Because
it's a
remember
derivative,
you
but-
told me, like right here, you asked about this d prime.
Sure.
That d can't stay with d prime, we have to divide by it. So since there's two d's here, d squared's derivative is 2d times d prime. Just like it's 2y dy dx. So you have to account for that y, or account for the d, and d is equal to this. So all we did was replace d with what it's equal to. So our problem is in terms of all x's. Because you can't type into a calculator x's and d's. So you have 3 critical points. How do I know which one's the closest one to what I'm asking for? Logically, I can eliminate one of them right away. I'm asking which point on the parabola is closest to 1, 4. So here's 1, 4. What point on that parabola is logically going to be the closest? First off, is negative 1.74 over here going to be close to 1, 4? No. Logically, one of these two is going to be closer to 1, 4, right? Get it? Okay. Pause then. Type this into 1, 1 on your calculator. I'm not going to make you find the zeros, but type that in, because you need to be able to find the signs.
can we just type in the 2x cubed minus 7x?
No. Well, I guess, because you know a square root's always going to be positive. And all we care about is the sign. What'd you ask?
I'm good now.
Okay.
I couldn't tell.
Like what something was?
Yeah. That's a weird neon color.
It is. I don't. Yeah. I don't know why I randomly decided to use that. So, let's talk about the graph now. So you have the graphing on your calculator. Go to second table. And what you need to do is you need to look at the signs of the y values around these 3 points. So in order to determine if something is a min or a max, and if we're trying to find the point closest, we're trying to minimize our point, right? So we're looking for the minimum. We need to know which one of these is a min. So how do you determine if it's a min? You need a sign chart. Well, how would you determine the signs? You'd go to the table and you'd look around these 3 critical points. So you would look around negative 1.794. So what's like to the left of negative, or what's happening at negative 2? The sign is, okay. What's happening, so we need to be between negative 1.74 and negative 0.143, so I'd be like negative 1. What's the sign at negative 1? Okay, we need to be between negative 0.13 or 0.143 and 1.938, so what's the sign between them? Maybe at 0 or 1. Okay, and then what's the sign bigger than 1.98? So at 2, what's the sign at 2? Okay, so my time chart says it goes negative to positive. So it's decreasing, then increasing, then decreasing, then increasing. So the distance is at a minimum at negative 1.794 and 1.938. We're trying to look for 1, 4. So of those 2 points, which one's going to be closer to 1, 4? So therefore, 1.938 is our answer. So 1.938, 3.755 is a point on y equals x squared that is close to the 0.14 hanging out in the world. So we found the pink dot looking for the distance closest to the black dot. We found the pink dot, which is the closest point on our parabola to the black dot. Yay, nay? I actually think the distance, the points and distance are the hardest problems. Okay?
What does the sign chart say?
That 1.938 is a minimum. And in order to be the closest point on a graph, it needs to be a minimum.
Why does it need to be a minimum?
Because if it's a maximum, it would be the furthest point on the graph.
That doesn't make much sense. If it's the derivative, isn't that the point where it crosses the axis?
Yes, it's a 0.
But that point's nowhere close to 0.
But that's not the point that we're saying is close. We're saying the 1.938 on that original x squared is close to 1, 4. Okay. Sine. Or do you have a different one in there?
Where's the smallest slope?
Skip it for now. Good. We'll cover it in a minute. All right. A rectangle, so looking at example 5, a rectangle is to be inscribed under the arch of a curve. What is the largest possible area the rectangle can have, and what dimensions give that area? So our curve is sine. So what do we know about sine? Yeah, like kind of goes up and then it comes back down. So where's sine at a max?
1 times pi.
Good.
Pi halves.
So sine goes through one cycle from 0 to pi, has a max at pi halves. And at pi halves, it's 1. So it says a rectangle is inscribed under the arch of our curve. So that means that there is a rectangle being drawn underneath that curve. What is the largest possible area that the rectangle could have? And what dimensions give that area? So what we have to do is we have to come up with a way of labeling the rectangle's area. Yeah, it's points. So area is length times width. That's great. So here's my length. How could I come up with a logical representation of that? So the entire length of the curve is what?
Pi.
Okay.
So it'd be pi minus whatever. You could label like the in between is like an x. So it'd be pi minus 2x.
Good. So what I would do is label the outsides of the rectangle as x between the curve and the rectangle. And we know that this is going to be symmetric, so that if it's x on this side, it's x on that side. So we can say that the length is pi minus 2x. So if the length is x, how do you find the height? What would this point right here be?
It would be x, whatever that is on the sine graph.
Whatever that is on the sine graph. Okay, so what does y represent?
The equation sine x.
So if it's x for the x value, you kind of just plug sine x in, right?
Yeah.
So this really represents the point sine x. Does that make sense? Because this is the curve sine x. So if the x value is x, then that point is sine x. So that y value represents the height. So that means the height is sine x. So the width or height is sine x. So area is equal to pi minus 2x sine x. The substitution work for everybody? So then I would distribute. So I'd have pi sine x minus 2x sine x. What's our end goal? Our end goal is a large area. So we need to maximize area. So how do you find the max of the area? We find when because that gives us a critical point, and then we take that critical point and confirm it on a side chart. Yes?
So this, how do you know? No, that's not what so you can do both the maximum and the minimum with the derivative?
Correct.
How do you know
Max
which
and mins occur at the zeros of the derivative.
How do you know which?
A sign chart. So, like, if it's positive, then negative, you have a max. Negative, then positive, you have a min. That means the original is going increasing to decreasing, so it makes it a max. Or it means the original is decreasing to increasing. So derivative of pi sine x is pi cosine x. So there's not a second part to the product rule because the derivative of pi would be 0. Because 0, pi is a constant. So you have pi cosine x minus, now here's the trick part, 2x sine x is a product rule. So you have to do the first times derivative of the second plus the second times derivative of the first, and then that negative distributes to both. That's the trick. It's not that we mess up the derivative, it's that we lose our negative. So you get pi cosine x minus 2x cosine x minus 2 sine x. Good, bless you. So this is really the same as pi minus 2x. Oh, there's that length coming back into play again. Cosine x minus 2 sine x. Once again, a lot of optimization problems are calculator problems. These are not pretty nice, neat numbers. You have to plug them into a formula and get the zeros. So go ahead, use your y equals, plug in that equation, and you can plug in either the middle or the bottom and find your zero.
We're trying to find when x is 0.
We are trying to find, yes, when x is 0.
There's a lot.
Yes, but there's only one that's in our
Range.
exactly.
What's our range again? Is it 0 to pi?
You asked, but you know the answers. It's 0 to pi because we're talking about the very, very first inscribed circle. So the length is no greater than pi. So what's the only one between 0 and pi? Did you change your window? What did you make it? 0 to pi? Yeah. Okay. All right. So here's the next question. Pause for 1 minute. Can I steal this? Because I didn't plug it in my calculator. Pause. Look at this. You know how you said there's a lot of them? And Michael, you asked me, how do we know which are which? This is the graph of the derivative. This is the graph of the derivative, because she's trying to find the zeros.
Is that just from 0 to pi?
Yes. So this is the graph of the derivative from 0 to pi. There's only one right answer for a maximum. How do we determine if something is a max?
When it goes from positive to negative.
Exactly. Why do we know that? Because we know that it means it goes from increasing to decreasing.
So that's
So there are two critical points. The first critical point would represent the biggest or the maximum, right? The second critical point would represent the minimum. So this point right here represents the biggest rectangle you have. This point right here would represent the smallest rectangle you could have. So kind of cool. That's why when I saw your graph, I was like, wait, pause, dude. All you actually have to do then is find which zero.
The first.
Because it represents the, and that's what they're asking you for. So they don't even care about the other zero. You only have to, thank you, find the zero of the max. So it's sufficient to show that. How can we justify that that's a max? What would you say? How do you justify that point's the max? Dom kind of hinted at it, but what would be the true justification?
The change from positive to negative implies a critical, or implies a maximum point. Or the point's 0.71.
Yes, it's 0.71. So the point x equals 0.71 is a maximum because
In the range 0 to pi.
a prime, yeah, and they typically give you the range, so
Okay.
you would just reiterate it. That point is a maximum because a prime does what?
It changes from positive to negative,
And that's what they want.
which implies a maximum point.
The sign chart, this means nothing. The words mean everything. They don't grade sign charts. They grade words. Says what is the largest possible area the rectangle can have and what dimensions give the area. These 0.71 doesn't represent dimensions. 0.71 actually represents the x value we're going in. The dimensions are pi minus 2 times 0.71 and the sine of 0.71. So remember, numerical answers are just literally that. But in order to actually have the real dimensions, you would have to plug that in and get 1.722 and 0.652. The dimensions are actually 1.722 by 0.652. So do you see how the x value doesn't represent a dimension? It actually represents the length to the dimension starting point. Let's do another one. The AP questions on optimization, there are few and far. There are only like maybe 2 on the whole test, but they're always challenging. They're like this. They're like, oh, let's put a square inside a circle. Or let's put a rectangle under a curve. Or use the distance formula. They're not going to be the nice, pretty farmer example that you guys are like, oh, can't I just make it a... I'm like, yeah, it doesn't stay that nice. Just wanted you to see conceptually kind of what's happening. To be honest, even this one's kind of nice. So it says the top and bottom margins of a poster are 3 centimeters and the side margins are 2 centimeters. So they gave me that this distance from here to here is 3, and this distance from here to there is 2. If the area of the printed material, so the printed space is in here, so the area of the printed is 192, So let's say the area of the inside. Find the dimensions of the poster with the smallest area. So we are trying to minimize the area of the outside. So we have a minimum area on the inside. We have the margins that have to go with the poster. We want to minimize the amount of paper used. So what could you do to label that drawing to get to that idea? What could you do? Area is length times width. So what would this distance be here? It's our length, let's say, right? So I hate to use the letter L because I think it looks like a number, so I'm going to transform it to an X, right? So this would be X. What would the inside be? Or how would the outside relate to the inside? Go ahead.
X minus 4.
Yeah, so you could do X minus 4 for the interior, or you can make the inside X, and then the outside would become, yeah, I think negatives are rough too. So, but like, it doesn't matter. Both are right. You could flip-flop it any way you want. And that's kind of why I start with, like, if I make this X, what's the inside? If I make the inside X, what's the outside? Both work. So if I stick to the positive nature, if we call this X, then we'd call this probably Y. And then we would make the outside Y plus 6. Perfect. So again, the big mistake I see is that we tend to make it Y plus 3. And I purposely didn't label the margins on top and bottom. I only labeled one. But you nailed it. You got that it's plus 3 on top and on bottom. Plus 2 on right and on left. So if the inside area is XY, AI could be replaced with X times Y equals 192. We're minimizing AO, so I don't know AO. But length, we said, was X plus 4. And width is Y plus 6. So what's the problem I'm currently situated with this problem? My AO has 2 variables. So what do I have to do? Substitute something. Do you want to get rid of Y or you want to get rid of X? Let's get rid of Y. So to get rid of Y, we got to solve for Y. So Y in the original over here, given that's unchanging, is 192 over X. So AO is X plus 4, 192 over X, sounds like blood pressure, to plus 6. Oil it out. So what's nice about X times 192X? The X's cancel. X times 6. This one, not so nice. You get 4 times 192 all over X. 4 times 192 is 768. And then 6 times 4 is 24. How do I find a max or a min? What am I going to do? Find the max or the min area of that problem. Take the derivative. What's really nice about the derivative of 192? It's the derivative of 6x. What's the derivative of 768 all over x? So the only thing you have to do is add, it's a negative, because it would come up as x to the negative 1. So it becomes negative 768 all over x squared. What's the derivative of 24? What do we like to do if we have a fraction plus another number? Combine them. How do you combine them? Yep. So this becomes 6x squared minus 768 all over x squared. Why is that easier? Well, now this is really easy to find the zeros, right? What are the zeros of the base? So you got x equals 0. What would the zeros of the numerator be? Well,
786 divided by 6, taking the square root of it.
Yep, so 76 divided by 6. So do your math. It's not going to be a pretty number. So again, like I said, a majority of these are
11.314.
good. A majority of these are calculator problems for this reason. So we get x equals 0. Is it logical for the length of a poster to be 0? No. So obviously that answer is not accurate. That doesn't work. You cannot have a length of a poster as 0. So the only valid critical point is 11.314. So that means that the x dimension is 11.314 plus 4, because outside of the poster you have to add back the 4. That's the only reason making it 11 would be nice, or x would be nicer. It just, at some point then you have negatives. So it's 11.314, which is really 15.314. And then the y value is 192 over 11.314 plus 6. Because y is 192 over x. So you plug that in, add your 6. So your y value is 17.
I didn't write down my decimals like a dummy.
So 22.970. Because it was 16.97. That's what I was saying. Like, I didn't write down. I wrote 17. Like, I rounded it. 22.970. Good. So I feel like the culminating optimization problem has to be, do you have a cylinder or an open box? Cylinder.
Yeah, the open box is such a good one too. I should have left that on there.
Remember I shortened this unit? Open box is such a good one. So it says a cylindrical can is to be made to hold 1 liter of oil. Here's the ticket, and this is like if you remember your SATs, they love to ask you the question where you can't use the given piece of information. 1 liter isn't a volume type problem. So the cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So, cylindrical can. What are we trying to minimize? If we're trying to minimize the cost of the metal, what do you have to minimize?
Surface area.
Surface area. So they give you 1 liter, which is actually a cubic volume, but you have to minimize surface area. So 1 liter is really 1,000 cubic centimeters, but yet I'm minimizing surface area. So what's the surface area of a cylinder?
Derivative of the area. Or the volume.
Okay. But also just think about a cylinder. What's a cylinder made up of? What's on top and bottom? What? Two circles, right? So what's the area of a circle?
2 pi r squared.
So it'd be 2 pi r squared. What's the outside shape? So if I had a cylinder with the top and bottom, if you open a cylinder up,
It's the circumference times the height. So it'd be 2 pi r h.
perfect. So the outside of the cylinder is really a rectangle if you open it up flat. Because like if I fold, I mean I'm not doing a very good job folding my paper to look like the cylinder, but if you open it up, the top is the circumference. It's like taking a circle and opening it, and then the height. So 2 pi r h. So surface area is 2 pi r squared plus 2 pi r h. To minimize surface area, we need the derivative of it, but we don't want to take the derivative of it until we can get rid of a variable. So we said volume is given. I know it needs to hold 1 liter. 1 liter is 1,000 cubic centimeters. So I know the volume has to be 1,000 cubic centimeters. I know it does. So what's the volume of a cylinder?
It's just radius times height. Or not area times height. So 2 pi r, or pi r squared h.
Yes. And then we want to get surface area in terms of one variable. So let's solve for h. So surface area is 2 pi r squared plus 2 pi r, and then instead of h, 1,000 pi r squared. So what's kind of nice about that? Plus. So the 2 stays, but the pi's cancel, and r cancels. 2 times 1,000 is, pi's are gone, r is gone, all over r. Well, now the derivative of that isn't so bad. So SA prime, derivative of 2 pi r squared becomes 4 pi r. And derivative of 2,000 over r gives you negative 2,000 over r squared. To find your roots, I would make this 4 pi r cubed minus 2,000 all over r squared. A cubic's only going to have one answer. The bottom is 0. Can the radius of a cylinder be 0? No, so we can toss that out. So we get 0 equals 4 pi r cubed minus 2,000. So 2,000 divided by 4 pi equals r cubed. So the radius is the cube root of 2,000 over 4 pi, which is approximately 5.419. And then the radius is one dimension. What's the other dimension we need? Height. So you just plug radius in. go to 10.83.